So, in the last class we were looking at the various components in the engine, and we were trying to identify which component is handling compressibility flow, or in which component is compressibility effect very significant. And we used two criteria to decide whether the whether compressibility effect is significant or not. The first one was how much of the change in specific volume, namely delta V, is due to a change in pressure. This was one condition that we used. The other one was that the Mach number, which is the velocity flow speed divided by the speed of sound, should be approximately less than 0.3. That was our consideration, with the speed of sound being given as square root of gamma RT. And based on this condition, we decided that the combustor essentially in the combustor flow is incompressible. We were looking at the compressor and the turbine part of the engine, the fan, the compressor and the turbine part of the engine, and based on the axial velocity we could see that the Mach number based on axial velocity is going to be relatively low, because the temperature keeps increasing, and as the temperature increases the speed of sound also increases, but the axial velocity more or less is remaining constant or decreasing. So, which means that the Mach number is going to decrease. So, it would suggest based on criterion 2 that in the compressor and turbine the flow should be incompressible. However, based on criterion 1 and based on this curve that we have here, the increase in pressure and the increase in temperature, we are able to see that there is going to be a significant change in density or specific volume due to pressure, which seems to suggest that compressibility effect is significant. So, the second one is saying compressibility effect may not be significant, first one says compressibility effect is significant. This disagreement is due to the fact that we actually used only the axial velocity, and in the case of turbomachinery we need to use relative velocity or vector difference of the absolute velocity and the blade velocity, which is the relative velocity, is quite high in these cases. In fact, in the fan blade the flow is actually subsonic at the root of the blade and is actually supersonic at the tip of the blade. That is based on relative velocity, the speed is subsonic at the root and supersonic at the tip, which is why these are called transonic fan blades. Okay. Even in the other parts of the engine, you can see the RPM. You can see that, for example, the fan spins at an RPM of 3000, and there is a huge variation in the Mach number from root to tip. And the next system, which is the intermediate pressure system, spins at a speed of about 7500 RPM, and so if you calculate the velocity, relative velocity based on this speed, for this case also the Mach number will be more than 0.3. Right? And the high pressure system spins at an RPM of around 10,000, and you can see that the blade speed is even higher for that. So, which means that based on relative velocity, both the criterion, based on relative velocity, second criterion says that the flow compressibility effect is going to be significant. First criterion also states the same thing. So, there is really no disagreement. So, when it comes to applying this criterion for turbomachinery, we must be very careful and use the correct velocity, which is the relative velocity for these cases. In the nozzle, which is located over here, as we can see, the velocity increases and the temperature also decreases, although it is not clearly visible in this scale. The temperature decreases since the fluid undergoes an expansion process. So, the Mach number increases in the nozzle to reasonably high subsonic values, perhaps even Mach number 1, due to two reasons. One is the increase in the velocity, and two, the decrease in the speed of sound due to the decreasing temperature. So, both these effects together cause the Mach number to increase to values probably equal to the speed of sound at the exit of the nozzle. So, this tells us that if we go back to this, so this tells us that the flow or compressibility effect is minimal in the combustor, but compressibility effect is significant in the fan and the compressor, and compressibility effect is also significant in the turbine and the nozzle, right, except for the combustor. Compressibility effect is significant in the fan, compressor, turbine and nozzle, which is why we are going to study gas dynamics first, because compressibility effects are significant in almost all components except the combustor. That is why we are going to look at, we are going to start the course with gas dynamics. Okay. So, we will first take a look at the introduction, which we have already done. The introduction basically pertains to how do we assess compressibility, whether compressibility is significant or not in a flow, that we have already done, and we then move on to fundamental ideas, right, and then normal shocks. We will look at Rayleigh flow, flow with heat addition. So, in this particular chapter we will show that if compressibility effects are not significant and if you add heat to a flow, then the pressure remains constant. If compressibility effect is significant and you add heat to such a flow, then the pressure also increases along with the temperature, right. We will show that in this case. This is followed by fan of flow, where we have flow with friction, which is also very important and occurs in many practical applications. Then we will look at quasi one dimensional flows. The first two categories, the first three flows, normal shock, Rayleigh flow and fan of flow, would be 1D flow. Then we go to quasi one dimensional flow, where we allow for some variation in the other direction also. This would be typically flow through nozzles, flow through blade passages and so on. We then follow it up with study of oblique shocks, which also occurs in many turbomachinery applications like the ones that we are looking at. This is followed by Prandtl-Meyer wave. So, oblique shock is basically a compression wave. The Prandtl-Meyer wave can be both compression and expansion waves, but it is an isentropic process, in contrast to the oblique shock, which is not an isentropic process. So, we will discuss these things first. This will be followed by our discussion on propulsion. So, we start with the concept of thrust. We then look at different modes of propulsion. Basically, we will look at propeller versus jet as different modes of propulsion. Then we will look at the operation of a basic gas turbine engine, right. This will be followed by a discussion of turbojet, the afterburning turbojet and the turbofan engine. So, these are all basically derivatives of the turbojet engine, and we will look at the different parts of the gas turbine engine, namely the intake, the compressor, the combustor, and in the combustor we will look at emissions particularly. Then we will look at turbine, which in which the cooling materials in metallurgy is very important. Unless you cool the blades, you will not be able to handle the combustor, the post combustion gases which are coming at very high temperatures. So, we need to do special things to the turbine blades to make them operate in such a harsh environment. Then we look at nozzles, and then we move on to turbofan engine, where the additional component is the fan and the fan nozzle. We will discuss that. We will look at emerging trends in the industry. What is the latest and the greatest in the industry in terms of propulsion technology? What are the concepts that are being pursued? We will discuss that. Then we will move on to ramjet and turbo ramjet engine. Now, these are the ramjet engine, for example, is an engine without any moving parts, which means that the intake plays a very critical role in compressing the air. If you remember, we said that two things have to be done in jet propulsion, right. One is increasing the enthalpy and then converting the enthalpy to thrust. Increasing the enthalpy required us to increase the pressure and the temperature. Now, in a ramjet, the pressure is increased not by using a compressor, but by decelerating the air, because it is moving at such high speeds. If you decelerate the air properly, that can actually translate into a pressure rise. So, it operates without any compressor, which means you do not need a turbine also, right. But the intake has to be designed extremely carefully to make sure that you are able to get the kind of pressure rise that you are looking for. Okay. So, that is why we have identified supersonic intakes as a special topic for discussion. We will take a look at a scramjet engine, just a brief idea about the scramjet engine, some of the issues involved in scramjet engine and so on. Then we will go to the thrust equation. We will derive the thrust equation for the various engines, right. The idea is to calculate thrust produced by the engine and thrust specific fuel consumption. How much fuel does it require to produce, let us say 1 kilonewton of thrust, and those are the two quantities which are of interest. So, we will do a thermodynamic analysis, we will develop an equation for calculating thrust, and then we will actually use the equation to calculate the thrust produced by turbojet engine, turbofan engines and ramjet engines. Okay. In the first two cases, we will take engines which are actually in service today, actual engines in service, and we will do thrust calculation for those engines, so that This is not some conceptual engine that we are working on, but actual production engines, and we will compare the results from our thrust calculation with what the manufacturer reports. The manufacturers may report that this engine, if you remember I showed the Rolls-Royce engine, they said this produces 250 kilonewtons of thrust for example. We will actually do a calculation of that engine and see whether it produces 250 kilonewtons or not. Then we will try to compare some of the other performance metrics of that engine with what the manufacturer reports. Okay. Broadly speaking, that is what we are going to do in the course. So we start with gas dynamics. The importance of gas dynamics is I think brought out clearly. So now we will do gas dynamics, then move on to propulsion. Okay. Any questions? We will follow two textbooks, fundamentals of gas dynamics and fundamentals of propulsion. The exercise problems will be taken from the book, worked examples will also be taken from the book. Okay, so we will basically teach from these two textbooks. Okay. So we have already discussed the notion of compressibility. We now move on to the next topic, which is perfect gas equation of state. The equation of state for a perfect gas can be written as PV equal to RT, where P is the pressure, V is the specific volume. Now this constant, gas constant R, is actually the particular gas constant, and this is equal to the universal gas constant divided by the molecular weight of the gas. This is not the universal gas constant, but it is the particular gas constant, which is universal gas constant divided by the molecular weight of the gas. Okay. For air, for example, we will take the molecular weight to be 28.8 kilogram per kilomole. T here is the temperature. In the later part of the course, we will actually refer to this temperature as the static temperature. Okay. For now, temperature is sufficient and pressure is also sufficient, but as we go along, we will start calling the pressure static pressure, we will start calling the temperature static temperature. Okay. And I will make the definition clear as we go along. So R universal of course is 8314 kmol Kelvin. This equation can be written in many different forms, and if we use the fact that the specific volume is the reciprocal of the mass density, we can write P is equal to rho times R times T, right, where rho is the mass density in units of kg per meter cube. Or if I make use of the fact that the mass density rho itself is equal to the mass of the gas divided by the volume that it occupies, I can write this equation of state as PV equal to m times R times T. Now the concentration C, it can also be written in terms of a concentration. So concentration C is defined as the mass of the gas divided by the molecular weight per unit volume. So this is in units of kilomole per cubic meter, and in terms of the concentration we can write P is equal to m and if you recognize the fact that m divided by molecular weight, this quantity is equal to C, I can write this equation as P is equal to C R universal times T. It is also possible to replace the concentration. It is quite useful in certain types of applications to write this not in terms of concentration, but in terms of something called a number density. Okay? Number density n is defined like this. N is actually in units of, it tracks molecules per unit volume, and since 1 kilomole of a substance has how many molecules? Avogadro number of molecules, right? So, since 1 kilomole of a substance has Avogadro number of molecules, which is nothing but 6.023 times 10 to the 26 molecules, it has Avogadro number of molecules. I can actually rewrite this equation as P is equal to N times R universal divided by Na times T. So, I have replaced the concentration with, let me write it like this. So, N, the quantity N is equal to C times N Avogadro. Now, this quantity here is nothing but the Boltzmann's constant. So, I can write this as N times Kb times T. So, P equal to N times Kb times T is a form of the perfect gas equation, which is very useful in many applications, including flow of plasmas and so on. Right. Now, we need to know one more thing before we can proceed. So, we know how to relate the pressure, temperature and specific volume of the perfect gas. We also need to know how to calculate changes in internal energy of a perfect gas as it undergoes certain flow processes. Let us see how we do that. As we discussed earlier, the internal energy of a perfect gas is also a function of temperature and pressure. Let us see how this works. Just like we said that the specific volume of a perfect gas is a function of temperature and pressure, V equal to V of T comma P, we can also say that the specific internal energy which we will denote as E is also a function of T and P, where T is the temperature and P is the pressure. Now, for most gases, it turns out that the dependence on P is very weak. Which means that the internal energy is a strong function of temperature, but a very weak function of pressure. So, this means that I can write the internal energy as a function only of temperature. For all practical purposes, I can ignore the dependence on pressure and say that it is a function only of temperature. Right? Such gases are called thermally perfect gases. So, gases for which the internal energy is a function only of temperature are called thermally perfect gases. Now, depending upon the nature of this function, we can make a further idealization, which is what we are going to do next. So, now we are going to examine how the internal energy depends on temperature. What sort of a function is it? Is it a linear function, polynomial, quadratic? How does it depend on, or more complicated function? So, that is what we are going to look at next. Okay. Now, when we do that, we need to look at two things. Okay. How can store internal energy and how much So these are the two things that we need to know. How do actually gases store internal energy? So gases store internal energy in different modes. So the question that we wish to answer is the following. If I rewrite this, I can write the first question as how many different modes of energy storage are available, and question number 2, how much can be stored in each mode. The answer to the first question depends upon the nature of the gas. Let us say that we have a diatomic gas. This is easy to visualize actually than a monatomic gas, right? Let us say that we have a diatomic gas, right? Diatomic gas can be represented or depicted using the so called dumbbell model, right? You have all seen this exercise equipment, dumbbell. So this is used to represent diatomic gas. So let us say that we have, this is one molecule, this is another molecule, and the two are connected by through bonds, okay. So this is one molecule, this is another molecule, and this is a bond which connects the two molecules. This is called the dumbbell model, okay. So if you think about diatomic gas, let us say that it is at a temperature of 0 Kelvin. When it is at a temperature of 0 Kelvin, no internal energy is stored in the molecules. It is at a state of 0 energy. Now let us say that we slightly raise the temperature of the gas. The molecules, what do? The molecules begin to move, right? They begin to move with a translational kinetic energy. That is what happens first. So what is the first mode that we are talking about? The first mode in which the molecules can take up energy is the translational mode, right? So let us look at translational mode. Let us write down. So the first question is how many modes are available. So we are going to list out the modes that are available for storing energy by a molecule. The first mode, as we said, is the translational mode, right? So translational mode. Now when I say a translational mode, what exactly do I mean by that? Because when a gas molecule absorbs this energy, it is not constrained to move only in one coordinate direction. It can move this way, it can move in this coordinate direction, it can also move in this coordinate direction. That means it can acquire translational kinetic energy in each one of these three coordinate directions, right? So translational mode is the name of the mode, and within translational mode it can actually have three in number. So it can store translational mode in 3 in number, one for each coordinate direction. So we have heated the gas now, and as we keep heating the gas, it absorbs the energy and the molecules begin to move around with translational kinetic energy. Now as I keep doing this, the molecules are moving, and when I reach a temperature of about 15, till now the molecules are only moving with translational energy. When I reach a temperature of, let us say, 50 Kelvin or so, in most cases, then these molecules, because that energy is too much, that temperature is too much, so the molecules, in addition to moving around, also begin to rotate. Now till 50 Kelvin, the molecules are only translating. Now as you keep adding energy beyond 50, the molecules also slowly begin to spin like this, right? So now the molecules can also absorb the energy through rotational kinetic energy, right. That is the next mode that comes into play. 50 Kelvin is high enough for the rotational mode to become excited. This is what it is technically called, the rotational modes become excited. So now we have rotational mode also, in which the molecules can store energy. Now how many rotational modes can be there, right? One would think that again 3 rotational modes should be there, because the molecules can spin like this, right. So you have a molecule, it can spin like this, the molecules can also spin about this axis, and the molecules can spin about this axis. But if you look at the nature of the molecule, when it spins like this, it can have considerable energy. Now if it spins like this also, it can have considerable energy. But when the molecules spin about their own common axis like this, the energy is very small, because the moment of inertia of the molecule is very small. So effectively rotation gives only 2 modes. When the molecules rotate like this, they can have considerable energy, or if they rotate like this, they can have considerable energy, not when they rotate like this, because the moment of inertia is very small. As you know, rotational kinetic energy is 1/2 I omega square. So I is very small, so the amount of energy that can be stored in this way is very small. So rotation effectively gives rise to only 2 modes. This is beyond 50 Kelvin, right, beyond about approximately 50 Kelvin for most diatomic gases. Now let us say that we keep increasing the temperature, now it is molecules are translating, they are also now rotating in both the directions. When you begin to exceed 600 Kelvin, that temperature is high enough that now this bond, which actually acts like a spring, begins to vibrate. Now the vibrational mode begins to get excited, right. So in addition to moving and rotating, now it can also vibrate like this. So now it can store energy in the form of vibrational energy, right. So that is the next mode that comes into play. Now vibrational energy we cannot really count, because the energy levels of the vibrational energy are quantized. So depending upon how many levels you can excite, say if you go to 700 Kelvin, probably 10 vibrational levels can be excited. If you go to 1000 Kelvin, maybe 15. When you go to 2000, all the vibrational levels that are possible for a diatomic molecule will get fully excited, right. So this is quantized, so we can't really give this a priori, and this happens beyond 600 Kelvin. So you can see that the internal energy of the molecules for the kind of temperature ranges that we are looking at is going to have translational modes 3 in number, rotational modes 2 in number, and vibrational modes. Even vibrational modes we will not actually consider for the sake of the course, because this allows us to make certain simplifications. Okay. So this tells us the number of modes in which the energy can be stored. So that answers the first question. Now we are going to look at the second question. Okay. Second question can be answered by using equipartition principle. Equipartition principle comes from classical theory, and it is not entirely correct, but it is good enough for our purposes. Equipartition principle states that each mode contributes 1/2 RT to the internal energy per unit mass. Okay. Actually, we said that these energy levels are quantized. In reality, these energy levels are also quantized. These are also quantized, but the spacing between the levels is so small that for all intents and purposes that quantization is not visible. So we essentially assume it to be continuous and use classical theory for describing this. Okay. In reality these are also quantized. In fact, when people realized that higher temperatures they were not able to account for this energy, that was one of the most important things that actually brought out the birth of quantum mechanics, when some things could not be explained using classical theory, this being one of that. This was the beginning of quantum mechanics. That was when people realized that you cannot store energy continuously, that it is quantized. Right? So we will not go into this part of it, we will try to stay in this part of this, and we will use actually equipartition theory to calculate our internal energy. So this answers our second question. First question, how many modes we have now. Second question, how much can be stored per mode, that is answered by this. So if we stay at temperatures below 600 Kelvin or so, for temperature less than 600 Kelvin, I can say that E, the specific internal energy for a diatomic gas, it is going to have 5 degrees of freedom. So I am going to have 3 times 1/2 RT from translational mode plus 2 times 1/2 RT from rotational mode. So this is translational mode and this is rotational. So this is equal to 5/2 RT for a diatomic gas. Right. Now if you think about a monatomic gas, you can easily see that a monatomic gas in which these things are absent will have only kinetic energy. Right, you will have only kinetic energy, there will be no rotational or vibrational energy. So we can easily write down that this is going to be 3/2. So 3 modes of translational kinetic energy. So for a monatomic gas, E is going to be 3/2 RT. Right? So that is the internal energy. The specific enthalpy, as you know, H is nothing but E plus PV, and since the gas obeys perfect gas equation of state, I can write this as E plus RT. So the specific enthalpy of a diatomic gas is going to be 5/2 RT plus RT, which is nothing but 7/2 RT, and 5/2 RT for a monatomic gas. So if you remember, we said that for gases for which the internal energy is a function of temperature only, these are called thermally perfect gases. And we can see from here that not only is internal energy a function of temperature only, it is also a linear function of temperature. As you can see, internal energy is a linear function of temperature. So such gases are called calorically perfect also. Okay. So if E is linear in temperature, then these are called, such gases are called calorically perfect. And in our course we will assume the gases to be calorically perfect throughout. That allows us to calculate the internal energy using such formulas. So having calculated the specific internal energy and the specific enthalpy, I can write CV, which is nothing but partial E partial T, or constant volume is also okay, right. So, this is going to be nothing but 5/2 R for a monatomic gas, I am sorry, for a diatomic gas, and this is going to be equal to 3/2 R for a monatomic gas. And similarly for Cp also. So, if I write Cp, which is nothing but partial H partial T, this is equal to 7/2 R for a diatomic gas, and this is equal to 5/2 R for a monatomic gas. Which then allows me to calculate or determine the ratio of specific heats of the gases, which is a very important quantity in gas dynamics. So, the ratio of specific heats gamma for a diatomic gas ratio of, or for any gas, the ratio of specific heats is nothing but Cp over Cv. And if you use these expressions for Cp and Cv, we have that Cp over Cv for a diatomic gas is 7/2 and it is equal to 5/3 for a monatomic gas. I am sorry, it is 7/5, thank you. Is 7/5 for a diatomic gas and 5/3 for a monatomic gas, and since we use air as the working substance in all our calculations, we will assume gamma to be 1.4 throughout. 7/5 for most diatomic gases actually is quite a good approximation. We can use it quite well. It is also easy to show from these relationships. Cp minus Cv is equal to R, which is the so called Myers relation. Okay, any questions? So, the variation of Cp and Cv with temperature can be seen from here. Let us take a look at that. So, here you are looking at variation of Cv over R with temperature, and you can see that initially the translational mode gets excited and the amount of energy that we can store increases until it reaches 3/2, right. So, that corresponds to 3 degrees of translational mode. So, it becomes 3/2 at about temperatures around 3 Kelvin for a gas. So, at about 3 Kelvin the translational mode is fully excited. Then as we keep increasing the temperature, it remains at 3/2 and then it begins to increase as the rotational modes begin to get excited. And once we reach temperatures beyond 50 Kelvin, the amount of energy that is stored in rotational mode is also reaching a maximum. So, now the molecules are rotating with the highest possible kinetic energies, and then it reaches till about 600 Kelvin. You can see that the Cv by R remains constant at 5/2. Now, once we go beyond 600, you can see that the energy that can be stored in vibrational modes begins to increase, and the curve continues to increase this way. And then as we keep going, additional modes of energy like electronic modes become available for the gas to store the energy in. But we will stay in this range of temperature about 50 to 600 Kelvin, where the Cv over R is constant and is equal to 5/2 R. So, the calorically perfect assumption is valid in this region, and that is the region in which we will stay mostly. Okay. Even if the temperatures become high, for the purposes of this course we can essentially assume the Cv to be constant, then we can do calculations that way, or use slightly different values for combustion gases which can be at higher temperature. Later on when we do calculations, engine calculations, the gases that come out of the combustor are at a higher temperature. So, Cv over R is not 5/2 for that gas. We will assume a slightly different value for that and do our calculations. Okay. It is a good enough approximation. Okay. So, that completes our introduction introductory ideas in gas dynamics. What we will do next is look at some basic concepts, one dimensional flow basic concepts. Let us do that. So we start with one dimensional flows. So the governing equations for one dimensional compressible flow, four governing equations are available. First one is the mass conservation equation, which says that, so this is the so called continuity equation. Rho is the mass density and u is the velocity. There is only one velocity component because we are looking at a one dimensional flow, right. Now the momentum equation can be written like this: dp plus rho u du equal to 0. This is the momentum equation. P is the pressure, and the energy equation looks like this: dH plus d of 2 equal to 0. This is the energy equation. Notice that here we assume the fluid to be a calorically perfect fluid without any viscosity. So there is no effect due to viscosity of the fluid, and the fluid is also calorically perfect. Okay. H is the specific enthalpy, and this is the energy equation. In addition to this, in such flows we also need to write down the change in specific entropy. ds can be written as delta Q over T plus delta sigma irreversibility. Sigma irreversibility is the entropy that is produced due to irreversibilities in the flow, and it is non-zero and positive when there is irreversibility in the flow, and it is equal to 0 when there are no irreversibilities in the flow. Let us write that down. Is greater than 0 when irreversibilities are present, and it is equal to 0 when reversible, or we can also say irreversibilities are absent. We can say this is not a quantity that can be measured, but it allows us to determine whether entropy is going to increase or remain the same in a flow, right. We can use other means of calculating entropy changes in the flow, but this gives us a very good idea of whether which direction entropy change is going to go. Okay. The first term here talks about entropy. This is due to heat interaction, so this means this is the entropy that we are transferring to the flow or taking away from the flow, right. If you give heat to the flow, then its entropy, as you can see, is going to increase. Delta Q is positive, so that means this is entropy transfer. If you remove heat from the flow, then the entropy in the flow is going to decrease. So this is entropy transfer, and the second term is entropy production, right. If there are irreversibilities in the flow, then that is going to generate entropy, and if there are no irreversibilities in the flow, then there is no generation of entropy. So the entropy change in a flow as you go from one point to another is due to two things: one, entropy transfer, another one, entropy production, right. If it is an adiabatic flow, then there is no entropy transfer, delta Q is 0, right. So that means for an adiabatic flow, the entropy can only increase or increase or remain the same. There is no question of decreasing for an entropy for an adiabatic flow. So, for an adiabatic flow, delta Q is 0, and so ds is, so ds can increase or at best remain the same okay, because sigma is always positive or equal to 0. So, that means entropy in an adiabatic flow can increase or remain the same. Okay. So, these are the 4 governing equations for the flow, and we are going to look at in one after other solutions to these governing equations. These governing equations permit different types of solutions, okay, and we are going to, some of the types of solutions that they permit is that wave solution is permitted. So, a wave is actually a discontinuity. Flow properties ahead of the wave have a certain value, flow properties downstream of the wave have a certain value. So, the wave itself is a discontinuity. Gas dynamics is probably the only application where discontinuous solutions are permitted. Okay. So, this is a discontinuous solution, discontinuity. Other solutions are also permitted. These are continuous solutions. For example, the wave solution will encompass things like an acoustic wave propagation, or it can also be a normal shock wave. And the continuous solutions, under continuous solutions we are going to look at a Rayleigh flow and Fanov flow. So, these are the 4 solutions that we will look at one after the other. Okay. 2 under the category of wave or discontinuous solutions, and 2 under the category of continuous solutions, which is going to be Rayleigh flow or Fanov flow. Okay. We will pick this up in the next class.